All right. Hey, Justin. Can you see and hear me?
Yes, hi guys.
All right.
I can hear you. Okay, great. Welcome everyone to the Eth Proofs Day demo. And I want to give a massive thanks to Will, who has worked extremely hard on today's event and is just generally shipping so many great things. So today is a bit of a special day. It's new territory that we'll be stepping onto. It's a small step for my validator node and a giant leap for Ethereum L1. So today's presentation will be split into three parts. First of all, I'd like to share a little of context about what is happening, and then jump into the live demo, and then finally say thanks and give kudos to many of the teams that were critical for the success of this demo. Okay, so if you zoom out, we're entering a new paradigm where we're moving from execution proofs execution clients to execution proofs. Execution clients are extremely heavy pieces of infrastructure that have to re-download every single transaction and replay them, and requires gigabytes of RAM, terabytes of disk, very sophisticated SSDs called NVMe drives, as well as many CPU cores. With execution proofs, we have a much more lightweight setup where you don't even need to download the proofs. It suffices to do data availability sampling, and you also don't need to re-execute the proofs. So this is my home setup. I'm actually giving the talk on my staking laptop, which is an old MacBook Air. I have a consensus node, which is running Lighthouse. I have an execution client running Geth. And I also have two other clients, what's called a validator client, which is also Lighthouse, and a sequencing client. Here I'm running an alternative to MevBoost called Commit Boost, which I really like. Now, the three of the clients here are very scalable in the sense that when you increase the gas limit, they won't break a sweat and they'll be able to handle the throughput. But we have one strandler here, which is the execution client, which is a massive bottleneck towards the gigagas frontier. So the hope here is to remove the execution layer clients and replace them by execution proofs, thereby also removing the bottleneck. Hence the title of this slide, Dev Disconnect. And what I'll be focusing on in the demo today with the terminal logs is these two portions here, the two Lighthouse clients, both the beacon node and the validator client. So what we did for this demo is that we started with Lighthouse and we made it zk. What exactly does this mean? It means that we added a new flag, -- execution proofs, which when you put on your command line will listen to a new gossip channel, also called execution proofs, and we'll be listening for zkEVM proofs and using those as our source of truth. And I'd like to say thanks to Kev, who has drafted the initial version of zk Lighthouse, Dapline, who reviewed Kev's work, and Farah, who finished the end-to-end demo based on zk Lighthouse. So today we're going to have 7 different proving clusters, proving every single block, and that's across 4 different zkVMs. 5 different zkVMs, sorry. We have 4 here, Airbender, OpenVM, Pico, SQ1 Hypercube, and we have another zkVM called Zisk, which is being proven not only by the corresponding team in Spain, but also by an independent prover here called zk Cloud. And what these proving clusters have is that they have different sizes. So the number on the left here represents the number of machines that the clusters have, and the number on the right here represents the number of GPUs. So there's a wide range of number of GPUs. Airbender, for example, has 2 GPUs, and OpenVM, for example, has 32 GPUs. Now, when I was thinking of doing this demo, I didn't think we would have 7 different proving clusters. I thought we have 3, maybe 4. So this is really an excellent outcome. And not only that, 3 of the clusters are using 16 GPUs or less, and therefore are under the 10 kilowatt target that we set ourselves. So congratulations to Airbender, SP1, Hypercube, and Zisk for reaching that target. And I believe that OpenVM and Pico will reach it very, very soon, possibly next week, maybe next month. We'll see. So what these proving clusters are doing is that they're submitting as quickly as possible proofs of L1 mainnet EVM blocks onto Eth Proofs. Those proofs get forwarded to a gossiping node. The proofs then get gossiped to this new subnet in purple. And then in yellow is my home validator node running, again, a modified version of Lighthouse and using the zkEVM proofs as the source of truth. Okay, let's try the demo. Let's see if it works. It's not completely production grade, so I don't recommend you to try this at home unless you want to be an early adopter, in which case do DM me or Farah and we'll try and get you hooked up. So I just want to briefly tell you what I'm about to show you. So I'm going to load ethproofs.org and show you all of the beautiful zkEVM diversity that we have. I'm going to be showing you my beacon node, which is running right now on this computer, the validator client, which is also running right now on this computer. I'll be switching to Beacon Chain, which is a block explorer for validators. And then I'll be showing you the beacon node again, but this time showing you the boot up phase. Okay, let's move to ethproofs.org. Okay, so just going to reload the page real quick. This is a new landing page that we have for Eth Proofs. So here we have a slot number 895, and you can see the proofs are gradually during the slot being downloaded and verified. zkSync Airbender is only shown as proved, not verified, because we haven't yet integrated the verifier, but that will be fixed shortly. And so, yeah, it's a really fun page, which is super dynamic, and I recommend you have a look. Okay, next up, what do we have? We have the beacon node. So this is the my beacon node. We have some new Eth proof logs. So I hope the font is not too small, but basically we're downloading a bunch of proofs, and let's search for this keyword verification. So when we receive a proof, we have verification started. When we've verified the proof, we have verification completed. So here in this case, we have a Zisk proof from a ZK Cloud. It came for slot 957, and we received it at millisecond 550, verified at millisecond 568. So it took 18 milliseconds to verify on my laptop. And if we search for the slot number here, you can see that for this specific slot, I've received multiple proofs. And there's a very important message here, which says minimum required execution proofs received. So in order for a block to be considered valid by my beacon node, I need to have 3 zkEVM proofs downloaded. And so in this case here, I have proofs for proof IDs 7, 6, and 5, which corresponds to Pico, Zisk, and Zisk from ZK Cloud. And as soon as we receive that, the block is again considered valid. And another thing worth highlighting is that as soon as a proof is accepted, meaning that the proof has been verified, it is then gossiped to all of the other peers. So this is a peer-to-peer gossip network for these various proofs. And then one final thing that I wanted to show you real quick is that we have these synced messages. which are exactly the same as a normal beacon node, with one exception here, which is the block is shown as empty. And the reason here is that this is the head block, and it's not being validated in real time. There's a little bit of a delay in order to receive the proofs. It's roughly a 1 slot delay, and so the verified head is empty here, and that's going to be important later. Okay, let's hop onto the validator client. So here, not much is happening. We have info log telling me that my validators are active and I'm connected to the beacon nodes, and I'm successfully publishing attestations, which is exactly what we want. Now, let me move on to beacon chain. So this is my validator, and one thing I wanted to show you here is the different attestations that I've been making recently. So here, if we look at the latest attestation, I have the correct. I got rewards for the source, the target, but not the head vote. I don't know if you can see it says 0 Gwei there, and this is to be expected because I'm publishing attestations late because I'm waiting for the zkEVM proofs, and I'm getting penalized because I'm not getting this timeliness reward for voting on the head immediately. So right now, what I'm doing is a little bit of irrational behavior. Even though there's, I guess, 2 things to say. The first one is that this will be fixed with delayed execution, and 2, I can run on much lower cost hardware, and so since I only have one validator, it might actually be rational for me to lose a little bit of rewards for the head vote, but make it up on the hardware. Okay, let's see what we have next. Yeah, I wanted to show you that my beacon score is pretty terrible in the last 30 days. And part of the reason is that we've been doing a lot of testing in the last couple of weeks, and I've had a lot of downtime. Okay, now one final thing that I wanted to show you is the beacon node boot up. So here we have the various flags that I'm using. I'm specifying a specific boot node and a trusted peer ID. So this is all networking stuff. And the reason is that right now there's only 2 nodes in the peer-to-peer network that are understanding the proofs. And so they need to be directly paired, which is what this is all about. I have the staking flag because I'm staking. And I also have the execution proofs flag for which is new for this demo. And when you load things, you'll see that there's an info log here which says we're running with execution proofs, meaning that no EL is needed for proof verification. And shortly we should be seeing here that I'm subscribed to a new topic. So this is an info log saying which topics I'm subscribed to, and here, if you can see it, we have a new topic called execution proofs. So that's it for the demo today. It seemed to have worked great, and you see already we're receiving proofs and verifying them locally on my computer. Okay, back to the presentation. So I just want to wrap this up by saying, congratulations to many of the teams. First of all, I'd like to congratulate all of the teams that have integrated with Eth Proofs. So we have 13 different teams, and we're expecting 2 more, Sino and Jolt, to integrate this year. It's pretty amazing that the Eth Proof project is less than 10 months old, and it's been such a success so far. There's a few teams that didn't participate in the demo, but I do want to give them a shout out. So for example, Powder is working on these really cool auto precompiles, and Zyren is the only team that has decided to experiment with something other than RISC-V. So they've gone with MIPS, which is a great data point to have. And I also want to give a shout out to some of our independent provers, Fermat, Seisig, Marlin, Snarkify, and Zilkworm. And Zilkworm in particular is doing something interesting because they're trying a different so-called guest program, specifically EVM1, as an alternative to our EVM and Ref. Okay, so in terms of those who did participate in the demo, we have SP1 Hypercube. It's really amazing that they reached the 10 kilowatt goal. They're also going to make the GPU accelerator source available very, very soon. And one thing which I only learned recently is that they've made a big effort on formal verification and have formally verified a very large subset of the circuits, which is something that many other teams will have to do and follow their lead. We also have the Pico zkEVM by Brevis. Two things that I wanted to highlight is that they will very, very soon be running on 16 GPUs as well. It was a little bit unfortunate that they were receiving their hardware a little bit too late, and they will also be open sourcing their GPU extremely, extremely soon. So shout out to Succinct and Pico. We also have OpenVM that gets bonus points for being fully MIT and Apache 2.0 open source and for being post-quantum. And we have the Airbender team that has done a couple of interesting things. The first one is that they have a completely from scratch guest program called zkSync So the only team currently, the one of two teams that are not using our EVM alongside Zilkworm. And by having this new implementation, they've managed to get the proving of every single Ethereum block on just 2 GPUs, which is really, really impressive and really portends very well for the future, because a lot of the other teams will be able to learn from the tricks that they have up their sleeve. And then finally, we have Zisk, which has the most bonus points. So massive congrats to the Zisk team. They're fully open source. They're targeting 128 bits of security. Their proof sizes are under 300 kilobytes. They're post-quantum. They've reached the 10 kilowatt power draw goal, and they've also built their own on-prem cluster. So over the course of a couple of weeks, they built this cluster, which seems to be in a small kind of room in some sort of a basement somewhere. The whole setup cost them less than $100,000, and they have 16 GPUs, 1 GPU per machine there. So this is a really, really cool outcome. Congratulations to this team as well. And this is my final slide. I just wanted to highlight a couple of things. First of all, highlighting that we have this new team, as Will said, with Farah leading. Farah has only been with us for 3 weeks, but she's already made herself essential to the GigaGas effort. And we're looking to hire a GigaGas champion that would be someone who is extremely technical, but also has the social chops to make some sort of a social intervention to try and convince as many people that this is indeed the future and have everyone rowing in the same direction. So feel free to email us, gigagas@ethereum.org. That's it. Thank you so much. Just prove it.
Yeah. Hey, congrats to everyone. So I forgot to plug the QR code here for Q&A. If anyone has questions, we've got 5 minutes set aside here. That will go to the Meerkat, and we can ask Justin a couple questions if there's anything that is on the top of your mind. So we just received the first question. Justin, you still able to hear me?
Yeah, I can hear you.
Okay, great. The question is, why the push for proving on consumer hardware? Shouldn't the emphasis be on fast verification and let block builders run fancy proving hardware?
Yeah, so we absolutely need the fast verification, and that's something that the snarks give us. I showed in the logs, verification on the order of 18 milliseconds. This is actually quite unoptimized, and I expect it to be single-digit milliseconds very soon. Now, in terms of the prover side of things, we have what's called a 1 of n assumption, meaning that we only need one prover per proof system to be online and producing the proofs for all of Ethereum. But we want the n to be very, very large. And in particular, we don't want to depend on data centers. And today we have, roughly speaking, 100 data center operators around the world. And so it's plausible, in a very extreme situation that all of them would simultaneously want to censor Ethereum proving, which is why we want to have this fallback of home proving and increase this number n from 100 to thousands, if not tens of thousands. So you can think of it as very similar to a trusted setup where we have a 1 out of n assumption, and we want the n to be as large as possible.
Great. We have another question, a couple coming in. So can I, as an individual, submit proofs to Eth Proofs?
Yes, you can. So contact Farah, Will, or me. We'll give you an API endpoint. Right now, what's happening is that the proofs go through Eth Proofs as this centralized choke point. But now that we have this new peer-to-peer gossip network, nothing prevents you from permissionlessly submitting the proofs on the new execution proofs gossip channel. And what I'm hoping will happen in a few weeks is that a lot of the provers will submit directly to the gossip channel, and that's going to shave maybe 1 or 2 seconds of latency that's introduced by having Eth Proofs in the middle.
Great. One more question, or another question. What do you think the timeline will be for the majority of the network's nodes to be running on Eth Proofs?
Yeah. So what I expect will happen roughly is that we'll have 1% participating in what's called phase 0, which is this early adopters phase, which will last from now to, let's say, mid 2026 or end of 2026. And then we'll have phase 1, where we will fix the incentive alignment with delayed execution. And here I expect about 10% of the validators to opt in. And then finally, phase 2, which is when 100% of the fully validated nodes need to opt in, because literally, these zkEVM proofs are part of the fork choice rule, part of the official consensus layer definition. So it will take a long time, as Will said. I'm hopeful that we can accelerate timelines, especially with a dedicated champion pushing the ball forward. I'm cautious with dates, but I would hope 2027 for phase 2, which is the mandatory proofs, is possible.
Oh yeah, they're asking me to go on stage, so I'm on camera view. All right, so maybe we'll do 2 more questions. So how does proving function under an economy of scale? Can 2 times the size prover prove more than 2 times a 1 times machine? Is there a benefit to a return on the economy of scale?
Yeah, so at the rough first approximation, because proving is so parallelizable, if you double the number of machines, you have twice the capacity to prove. Now, it's possible that there are economies of scale, if you're running a data center, but we're not really targeting that. We're not trying to unlock these economies of scale. What we're hoping to have is provers on a reasonable budget, which is $100,000, and a reasonable power draw, which is 10 kilowatts. And these numbers were highly inspired by electric cars. So if you buy a Tesla Model X, for example, it will cost you roughly $100,000, and your home charger will draw roughly 10 kilowatts.
Okay, great. Final question. Why not solve state expiry first? Yeah,
so these things are slightly unrelated. what we're trying to do here is ultimately increase the gas limit. But the zkEVM proofs lay the foundations for doing that. In some sense, state expiry is all about managing state after we've increased the gas limit. Now, when we have a very, very high gas limit, let's say, and we've reached 1 gigagas per second, state would grow fast if we were to keep things as is. And there's several solutions to our disposal. One is to have state be priced differently. So just like blobs are priced differently to gas, we can have state growth be priced differently and have an independent gas limit. We can also try state expiry. The other thing that we can try and do is just be a little bit more zen about it. And the reason is that today state growth is really problematic for the validators, which are assumed to be on weak devices. But with proofs, you're running statelessly. And so the fact that the state is large is not so much of a big deal. The two things that we care about with state are the size of the state. And here, if the state grows to terabytes, it's not a big deal because the cost per terabyte of NVMe drive is not that high. And that's certainly a cost that the provers can and the builders can handle. And then there's another issue that we care about, which is the latency to accessing state. And that the good news is that it grows logarithmically with the size of the state. Today we have unoptimized databases where the latency grows log squared with the size of the state. So that's something that we have to do, but it's totally traditional engineering. It's not moon math, and I'm hoping it's something that we can do over the months to come. And it's something that some of the clients, for example, eFrex, which is one of the new execution clients, they have, as I understand, a well-designed database that only grows logarithmically as opposed to log squared with the size of the state.
All right, thanks so much. Big round of applause for all the teams, contributors that were involved in